This question is about aromatic compounds. Part A. Phenol undergoes nitration more readily than benzene. Part 1. A student carries out the nitration of phenol with dilute nitric acid to produce 2-nitrophenol and 4-nitrophenol. A small amount of 3-nitrophenol is also produced. The student thought that a carbon-13 NMR spectroscopy could be used to distinguish between these 3 nitrophenols. Explain whether the student is correct. Let's start by identifying the number of carbon peaks in 2 and 3 nitrophenol. So if we start with 2-nitrophenol, we've got 1, 2, 3, 4, 5, 6, because it's an unsymmetrical compound. So it's got 6 carbon peaks. And then looking at 3-nitrophenol, it's also unsymmetrical, so we've got 1, 2, 3, 4, 5, 6 peaks. So it's got 6 carbon-13 NMR peaks. Then we can look at 4-nitrophenol, and this is a symmetrical compound, so we will have fewer peaks because we can draw a line of symmetry down the middle. So we've got 1, 2, 3, 4, because this is also 3 and 2. So it's got 4 carbon-13 NMR peaks, and then we need to link back to the question and say which one is distinguishable. We can identify which one's distinguishable by just writing a little sentence at the end of how many peaks are in which compound. So we can say that 4-nitrophenol is distinguishable and 2,3-nitrophenol is not distinguishable. To get your 3 marks for this question, you get a mark for saying how many carbon-13 NMR peaks are in 2 and 3-nitrophenol, so 6. You get a mark for saying how many carbon-13 NMR peaks are in 4-nitrophenol, so 4. And you get a mark for saying how you can distinguish between them based on this. So that 2 and 3-nitrophenol aren't distinguishable, but 4-nitrophenol is distinguishable. That gets you the 3rd mark. Part 2. Explain why phenol is nitrated more readily than benzene. So, if we decide to talk about how phenol is nitrated more easily than benzene, or more readily, so the first point is that phenol has a lone pair of electrons on the oxygen of the OH in phenol, and this lone pair is partially delocalized into the pi ring system, which is the circle that you draw in your structure. And this means that the electron density is going to increase if you're donating a pair or you're delocalizing a pair of electrons into a ring system. That's going to increase the electron density. And if the electron density is increased, this means that phenol will be more susceptible to electrophilic attack from electrophiles like your nitration of benzene or phenol in the part 1 or in part 2, which we'll come to in a minute, or part B. So to get the 3 marks for this question, there are 3 points that you need to have said. So you get your first mark from saying that phenol has a lone pair of electrons on oxygen, which is partially delocalized into the pi ring system. That's your first mark. Your second mark comes from saying that electron density is going to increase. So that's your second mark. And then your third mark is from saying that phenol is more susceptible to electrophilic attack. Part B. Methylbenzene reacts with sulfur trioxide, SO3, to form D, shown below. The electrophile in this reaction is SO3. Complete the mechanism for the formation of D, show curly arrows and the structure of the intermediate. So our first curly arrow in this mechanism is going to go from our increased electron density, so it's going to be quite negative, to our delta positive sulfur. So negative to positive. And then we're going to kick off this electron group onto our oxygen with the delta negative charge. And then this is going to form the negative that we can see in part D. And we'll have the intermediate with the structure that's going to look like this with our group we want to add. So our sulfur double bonded to an oxygen, double bonded to an oxygen, and singly bonded to an O negative. And we're going to have a hydrogen also attached here because there's hydrogens everywhere along this pi ring system or along the benzene ring. But there's only one because these have alternating double and single bonds. And we're going to have our CH3 group. This is important to keep the same. A lot of marks are lost from not including side chains like CH3 here. And our intermediate is going to have a half ring with a positive charge, which we can donate our hydrogen into. It's important with your half ring that it is in line with your points here and it doesn't go beyond them because then you won't get the marks. And this is everything because your hydrogen that you're putting back into this ring is going to produce your H plus here. So you can see how you've matched your intermediate to your product. So to get the 3 marks here, you get 1 mark for your curly arrows coming off of methylbenzene. You get 2 marks for having the correct intermediate with the correct arrow from your hydrogen to your positive ring. So that gets you 2 marks.